So I wanted to go through the example that we didn't finish in class and realized about 2 minutes after we got done with the video the other day that, our class the other day that, oh, well, I know how to do this now, I'm an idiot. So that's why this particular video is titled, Dr. Joe is an Idiot. So let's go back to these examples that we were talking about in class. In particular, we're trying to figure out whether or not these particular estimators are minimum variance unbiased estimators. So for this one again, we have a normal distribution. We know the mean, don't know the variance, and the question's asking is the maximum likelihood estimator of MVUE. All right, so we're not going to go through it, but it's not. If you remember our work that we did at the beginning of the semester for finding maximum likelihood estimators, this is the maximum likelihood estimator for sigma squared, knowing what mu is. All right, so let's find the Cramer-Rao lower bound first. Rather than writing sigma squared every time, in particular, since we have to differentiate with respect to the parameter, I'm going to use a theta for the sigma squared to start with. Here's our PDF for the normal, using, again, theta for the sigma squared. We take the log of it. So this is just taking the log of the PDF. I get the negative out in front because of the reciprocal. I get the 1/2 from the root. And I can break up this as a plus because of the product. Here, I would break up it as a product as well. And then the log and the exponential undo each other, which is why I just get the exponent here. We need to take a couple derivatives with respect to theta. First partial, notice that the log of 2 pi goes away, so I just get negative 1 over 2 theta. And then this one, I'm just differentiating with respect to theta, so I get a plus 1 over theta squared, and then the constant goes along for the ride. Second partial, again with respect to theta, so negative 1 over theta, its derivative is 1 over theta squared. 1 over theta squared, its derivative would be negative 2 over theta cubed, and the 2's cancel. So this is our second partial with respect to theta of the log of the PDF. Okay. All right, so now we need to do expected value. So expected value, here was our second derivative. This is a constant, this is a constant. So I can break it up to that point. So I get 1 over 2 theta squared, pull out the 1 over theta cubed in front, and I just have the expectation of the numerator. But I know the mean, so I'm doing the expected value of x minus mean quantity squared. That's the variance. So, and in this case, we used theta to represent the variance. So that expected value is theta. And so this simplifies to negative 1 over 2 theta squared. Fisher information is negative n times that expected value. Okay, so the negative will kill the negative. And I have that upside down. Sorry, this should be n over 2 theta squared. I have the reciprocal here. I got too excited before I went to the next step. This should be n over 2 theta squared. It should be reciprocated. All right, now we can figure out the Cramer-Rao lower bound. It's the reciprocal of the Fisher information, which this is correct. All right. Notice in this case that our theta was our sigma squared. So the variance of theta hat, or the variance of any estimator of the variance, will have to be 2 times the variance squared, or sigma to the 4th, over n. All right, so going back to the maximum likelihood estimator, and this is where things fell apart, and I was almost done and just needed to realize one thing, which is, again, why I'm an idiot. All right, so variance of the maximum likelihood estimator. So let's put that in here. I can pull the 1 over n out in front to get a 1 over n squared. The next thing we notice is that our x sub i's are independent. So and they're identically distributed. So each of these have the exact same distribution. So I might as well just say it's n times the variance of one of them. Well, when I do n times the variance of one of them, I get a 1 over n in front. Oh, look at this. Okay, so If I look at this and I divide it by, okay, so x is normal, subtract the mean. If I divide it by its standard deviation, I get standard normal. If I square a standard normal, I get a chi-squared. So I'm going to multiply top and bottom by the variance. And I'm going to pop the variance out in front. That's going to change it to a sigma to the fourth. This now on the inside is chi-squared of 1. So I know what its variance is. The variance of the chi-squared of one random variable is 2. So that gives me 2 sigma to the fourth over n, which, hey, by the way, that equals our Cramer-Rao lower bound. So the maximum likelihood estimator of the variance is a minimum variance unbiased estimator for sigma squared. So I was almost done. I was all the way to here and just needed to do that one more step to get to where I needed to be. I apologize for that. Like I said, I was frustrated and flustered with the video. I don't know why any more on Friday than I was any other day, but I know, excuses. Okay, so let's do another example. So you might be asking, well, why don't we use this typically then when we're trying to give us an estimate for the variance? Well, the problem is that notice to get the maximum likelihood estimator, we said that we had to know the mean of the distribution. How likely is it that we actually know the mean of the distribution? We probably don't. This is why we don't use this particular form of the variance, pardon me, because even though it's a minimum variance unbiased estimator for the variance, it just presumes that we know what the mean is to start with, which we typically don't. So let's instead go to the next example that was in the notes, which I skipped over in class, but this one won't take very long. So it's just the next one that's on the sheet that I sent out. So here's the sample variance. We already know it's an unbiased estimator, but let's show that it cannot attain the Cramer-Rao lower bound, and this just is a pet peeve of mine, that cannot is not the way you should write it. It's cannot. It's one word, but that's okay. Anyway, like I said, we already know that the sample variance is an unbiased estimator, and we also know that this particular random variable, when we multiply it by n minus 1 and divide it by sigma squared, we know that's chi-squared of n minus 1. All right, so let's look at the variance of this thing. All right, so the variance of s squared, I'm going to take the variance, the sample variance, and multiply it by sigma squared and divide it by n minus 1. So that I can see this piece that I know is chi-squared. So this part's chi-squared. This I'm going to pop out in front. Again, when we pop it out in front, it becomes squared. So I have the sigma to the fourth over n minus 1 squared times the variance of this other piece. We notice here that the other piece, the n minus 1 s squared over sigma squared, is chi-squared of n minus 1. Variance of chi-squared of n minus 1 is 2 times n minus 1. And then we simplify and we get 2 sigma to the fourth over n minus 1. No matter what n is, that's always strictly greater than your Cramer-Rao lower bound that we just did in the previous example. So the sample variance is not a minimum variance unbiased estimator in this case. But again, the point of this is that we use the sample variance to estimate the variance rather than the, well, what they call it, the empirical variance, I believe is what your book calls it, because even though the other one has a smaller variance, it presumes that we know the mean, right? And we don't know what the mean is in general. So that's why we use the sample variance to get our estimates for the population variance. Anyway, again, I apologize for the goof up in class, but hopefully this clears some things up for you and gives you another example with the Cramer-Rao lower bound.